Okay, welcome you all to this session of conduction and convection heat transfer. So far we have discussed the conduction heat transfer in a stationary medium which is a solid. This is because I told earlier that in fluid, if there is a temperature gradient, as we know that heat transfer is always associated with a temperature gradient. With a temperature gradient, motion sets in a fluid, even if there is no imposed motion by the external source. So therefore, solid is the only medium which can be considered as absolute rest or stationary, through which the conduction mode of heat transfer has been studied in detail, and we have analyzed both steady and unsteady heat transfer and steady one-dimensional and two-dimensional heat transfer. So now we will start the convection heat transfer. Today I will present before you a brief introduction of the convection heat transfer. Now convection heat transfer is referred to the phenomena when heat is transferred between a solid surface to its adjacent fluid which is in motion. Now fluid motion may be imposed by an external agency, fan, blower, when we call it as a forced convection, or if the fluid motion is self-induced by the temperature gradient due to the buoyancy, which we tell as buoyancy induced flow or buoyancy driven flow, then we call it as a free or natural convection. So therefore, this phenomena of heat transfer from a solid surface to its adjacent fluid in any direction depending upon the relative values of the temperature from solid to fluid or fluid to solid is referred to as convection heat transfer. So therefore, to understand the convection heat transfer, let us consider a simple case of flow of fluid past a flat surface, flat plate for example. Let us consider a flat surface. Let us consider a flat surface at a temperature Tw and a stream of cold fluid flowing through this past this surface with a temperature of T infinity which is less than Tw. Stream of cold fluid, it is cold fluid. As it flows past the solid surface, it will take the heat from the solid and it will be heated. So therefore, it is a common expectation that as the cold fluid flowing past the solid surface temperature is higher, heat is flowing from the solid surface to the cold fluid in this direction. At each and every point, we can represent this as the heat flux Q, heat flow per unit area. Now it is our common experience, everybody knows it, that if we increase the flow of the cold fluid, if you consider the cold fluid is flowing with a velocity of u infinity, if we increase the flow of the cold fluid, the plate is cooled faster. That means the rate of heat transfer or the heat flux is enhanced from the surface to the fluid, which means that this flow of fluid has got some effect in the transfer of heat from the surface. So this is the phenomenon of convection where the heat is transferred from the surface to the adjacent fluid, and at the same time the rate of heat transfer or the rate of heat flux depends on the flow of the fluid past it. If you decrease the velocity, the rate of heat transfer will be decreased. The plate will be cooled at a slower rate. Now to understand the mechanism, what happens here for the heat transfer, let us consider this in a much deeper sense, that let us consider that plate again with a temperature Tw at a fixed uniform temperature, Tw. Now, let me denote this u infinity as this scale, the velocity with which the fluid is approaching, and also I show a temperature scale of uniform temperature T infinity. Though temperature is a scalar quantity, I am showing it by the arrow just to have a representation like this, that with a temperature uniform T infinity which is lower than TW and with the U infinity approaches this plate. As we already know, please, do you hear to me? Is any problem? Now as we know, in fluid mechanics, which will be again told in details afterwards when we will have a recapitulation of the basic fluid mechanics, that the interaction between the fluid and the solid surface, and in consequence of the momentum transport in the fluid because of its property like viscosity and density, we know that there is a development of a layer that is known as boundary layer, which is a function of this distance if we consider this as x, in a sense that at any distance x from the leading edge, if we draw the velocity profile, it looks like this. That means the velocity changes in the direction parallel, perpendicular to the plate. Let us consider y within a thin region which is known as the boundary layer thickness. In fact, the velocity never reaches the u infinity free stream velocity, it approaches asymptotically, and we consider a thickness by giving a reference value of 99% of u infinity, but for our understanding, you consider better understanding that delta is the thickness where the u infinity is reached. So this is the velocity profile. It is always observed because of the two things. One is the surface fluid interactions, which usually, for usual surfaces in the domain of continuum, yields a no slip at the surface. That means the fluid velocity relative to surface is 0. If the surface is at rest, fluid velocity is 0. And it is observed that the velocity suddenly increases and within a short distance asymptotically merges to u infinity, and that is known as the boundary layer thickness. And this is because of the momentum transport and the retention of momentum played by the two important properties of the fluid, mu viscosity and the density rho, and their ratio mu by rho, as you know, the kinematic viscosity that decides how far the presence of the plate will be felt in terms of the velocity gradient. And as we know, it is little recapitulation of your basic understanding of hydrodynamic boundary layer, that tau, that shear stress at the plate, is given by minus mu del u del y at y is equal to 0. Okay. Similarly, let me write this thing that side. Tau is minus mu del u del y at y is equal to 0. At y is equal to 0 is the plate at any layer tau del u del y. That means the shear stress is confined within the layer boundary layer thickness where del u del y is there, but beyond the boundary layer thickness del u del y is 0, no shear stress is felt. This is the basic boundary layer. This is known as hydrodynamic boundary layer because of the momentum transport and the interaction between the solid surface and the fluid. Similar is the case for the heat transfer due to the temperature TW, which is different from T infinity, different from TW. In the similar fashion, if we draw the plate, we will see that a thermal boundary layer will grow, which is also a function of x, and like the velocity boundary layer in a sense that at a distance x from the leading edge, that this is the scale of T infinity, that means it is the scale TW. That means the temperature variation from the surface to the same way I draw it, the temperature also, the temperature variation is restricted within a small layer. In amplified way I have shown you, that is known as thermal boundary layer, so that beyond which the temperature gradient is 0 and the temperature merges with the free stream temperature T infinity from TW. So this is the growth of the thermal boundary layer, and this is a consequence of two things. Here also the surface to fluid interaction is that it requires a thermal equilibrium, so that at the surface the fluid temperature has to be the surface temperature, and the heat transport or the diffusion of heat in this direction, which is determined by thermal conductivity K along with the heat capacity, how much heat or thermal energy can be retained and how much can be transported, so that the temperature of the plate is felt away from the plate or influenced. That plate is influencing the free stream at what distance, that is determined by thermal conductivity mainly, and the rho Cp, that means specific heat, and the density. So depending upon these factors, a boundary layer, thermal boundary layer develops, which gives a temperature profile like this. Now this thermal boundary layer, delta T may be less than delta, may be greater than delta, hydrodynamic may be equal to delta. All cases are there. Here I have shown a case where delta T is greater than delta, and the ratio of these two, that is delta by delta T, is governed by the two important properties. Just as I have told you or explained you, it is proportional to nu, the kinematic viscosity, by alpha. What is that? Nu is nothing but mu by rho, and alpha is K by rho Cp. That means it is the ratio of the kinematic viscosity which is mu by rho. That means both mu and rho combinedly decide the diffusivity of the momentum. So the distance up to which the influence of plate will be felt. In the similar way, it is the thermal diffusivity, which is the ratio of thermal conductivity and rho Cp, heat capacity, which decides the diffusion of heat, how much it will diffuse, so that the influence of plate is felt, and their ratio will determine this ratio. This ratio may be greater than 1, less than 1, or equals to 1, depending upon the type of the fluid. This is the fluid property, and this is known as Prandtl number. At this moment, this is just an information for you, and this will be told in detail afterwards. Don't get discouraged that something is information, because in this class nothing will be information. All will be known in depth with the concept, but at the present moment it is an information that this ratio depends upon that. Now you see that here in this case the heat flux Q at any location x is written as minus K del T del Y. Now in convection heat transfer we are interested at the wall, heat flux at the wall. So this is at Y is equal to 0. And in fluid mechanics also we are interested at with the shear stress at the wall, not at any other plane, because that gives the total drag exerted by the fluid on the surface. So therefore this is Y is equal to 0. Now you see the two equations look very similar. Two equations look very similar, that the shear stress is proportional to velocity gradient with the factor of proportionality mu, coefficient of viscosity, and it is the thermal conductivity. So therefore you see for a fluid with given values of mu and k, both shear stress and the heat flux depends on velocity gradient and temperature gradient. So that controls the rate of heat flux and also the shear stress. For a comparison, I am writing this. Now rate of heat flux, that means heat flux at the solid surface, it is given there Q is by conduction, and by the Fourier heat conduction law QW is minus K del T del. Now consider a case when U infinity is increased. If U infinity is increased, what will happen? Now this can be written as tau is mu del U del Y. Now you write here del U del Y at y is equal to 0 scales as what? Change in U, change in Y, and that scales as U infinity by delta. This is the scale of del U del Y, U infinity by delta. Similar way here, the del T del Y, which scales as delta T delta Y, which is equal to TW minus T infinity divided by delta T. Now consider the case when the flow velocity is increased. That means if U infinity is increased, what will happen? We have already read in fluid mechanics, when flow velocity is increased, the hydrodynamic boundary layer thickness gets decreased. That means with more flow velocity, the diffusion of momentum is such that the influence of the free stream comes close to the plate. That means plate is incapable of giving its influence signal far away from this surface. So therefore an increase in U infinity delta is decreased. I give you for your recapitulation, which will be again done in this class as a review of fluid mechanics, that this delta hydrodynamic boundary layer thickness is proportional to 1 by root over Re. X is the local Reynolds number, delta is the local boundary layer thickness. If you remember, this Rex is U infinity x by nu. So therefore an increase in U infinity decreases the hydrodynamic boundary layer theory. And for a given Prandtl number, delta T is also reduced. So now first let us see here what happens, it is reduced. That means we see there is a tremendous reduction, increase in the velocity gradient. Velocity gradient becomes much more steep or increased, means shear stress is increased. That is why when the flow velocity is increased, shear stress is increased. Here what happens, since TW and T infinity remain same, so delta T is reduced with the increase in U infinity, because when delta is reduced, delta T is also reduced for a given fluid. So therefore the thermal boundary layer is reduced, which gives an results in an increased temperature gradient. So therefore we see clearly that with an increased velocity, both the temperature gradient and the velocity gradient is increased, and we have more shear stress and we have more heat flux at the surface. And this is the reason for which convection is considered, the phenomena of convection therefore is considered to be consisting of two things. One is conduction at the solid surface, conduction at solid surface, conduction at solid surface, plus advection due to flow away from solid surface, away from. So therefore we see that the convection phenomena is consisting of conduction at the solid surface and the advection away from the solid surface. And not only that, and they are related. So if we increase the advection, conduction is increased, enhanced, and if you decrease the advection, the conduction is decreased, the conduction heat transfer is decreased. And this is the reason for which I tell this we will not get in any book. I usually tell that convection mechanism wise is advection influenced conduction. In fact, I tell you, I don't know, you may find it in many books or some books you get this, that the convection is a phenomena which comprises conduction from the solid surface plus the advection in the fluid flow mainstream away from the solid surface. But I add this thing, convection is nothing but advection influenced conduction, because the heat transfer is basically by the conduction which is being affected by the advection. It is clear? You can find it geometrically also. Here if you draw a boundary layer which is lower in thickness, for example here in the second case the boundary layer thickness is reduced, and also this is the second case boundary layer thickness, and also your free stream velocity is increased. So you see this will be your velocity distribution, this line, so that this curve is steeper than this curve with respect to the y-axis. That means del u del y for this curve is more than this one. Similar is the case for del t del y. That can be geometrically seen, that if you have a delta t in the second case, then what you have? You have this thing, and the temperature free stream will reach here at the edge of this, and then it will. So the slope of this curve is more than this with respect to y. Del t del y is more in the second case, as it is found mathematically. Now after this, the very important, this is the basic mechanism of convection heat transfer. What happens is that it is basically conduction at the surface which is affected by the advection. That means heat is being pumped from the solid surface by conduction, and this pumping by conduction is influenced by the advection of the mainstream. Now in convection heat transfer, we define a quantity known as heat transfer coefficient. Now come to certain conventional terms and formality of convection heat transfer. Heat transfer coefficient. How the convection heat transfer is presented. This is the presentation of convection heat transfer. I will tell you in more details about this physical concept. Professor Suman Chakraborty also will follow after this class in theory. So, but heat transfer coefficient is a terminology we define in convection heat transfer coefficient as this heat flux divided by some reference temperature difference. If you make an analogy, I will tell you it is similar to, as I am not writing here, the skin friction coefficient with respect to fluid flow, which is defined as shear stress divided by a reference velocity head, half rho v square, reference velocity v. In the similar way, the heat transfer coefficient that you have already taught at fluid mechanics, Q by delta T reference. This Q is the heat flux and delta T reference is a reference temperature difference. And this delta T reference is actually the solid surface temperature, which is represented as TW wall. Wall means solid surface, which may be constant, may not be constant. For our understanding, we make it constant. In most of the cases, we deal with a constant solid surface minus a reference temperature, T reference. And this reference temperature, this is your whole life prescription, that this reference temperature is the free stream temperature in case of external flow. In case of external flow, like this, which today we are discussing as an example. And this T reference, the reference temperature, is the Tm. Tm is the bulk mean temperature. Bulk mean, this again will be taught afterwards. Today, along with the information, along with the concept, some information has to be there, how the convection is presented. for internal flow. That means flow through ducts. Now the bulk mean temperature concept is like this. I tell you, for example, a fluid is flowing through a cylindrical duct which has got a temperature TW at the surface, and fluid is cold initially. At any section we expect qualitatively a temperature gradient, like a temperature distribution like this. TW is higher than the fluid temperature. So a bulk mean temperature is the cross-sectionally average temperature based on the total thermal energy flux crossing a particular section. That means it is that constant temperature which is multiplied by the flow rate, and the Cp will give the actual thermal energy crossing that section. You understand? The way we define the average velocity. How do you define the average velocity? Sorry, this diagram is not. The average velocity, when there is a velocity distribution based on the volumetric flow. That is volumetric flow based average velocity. Similarly, it is the thermal energy flux based mean temperature, which is known as bulk mean temperature, which is the reference temperature. However, in our case, it is not much important, it is for your information. Now here, TW minus T reference in this case is TW minus T infinity. So therefore, in this case, I can write that H is Q by TW minus T infinity. And since Q heat flux is a local property which varies from point to point, so therefore H is a local property which varies from point to point. Therefore heat transfer coefficient at any location, local is defined as the local heat flux. Heat flux at that location, that is Q by A, heat transfer per unit area divided by this. Okay. Now if we relate this with the heat flux from the actual mechanism of heat transfer by Fourier heat conduction law, then it becomes equal to minus K del T del Y at Y is equal to 0 in this case, divided by TW minus T infinity. Again I am writing H. That means if you substitute Q by this, it becomes like that. So therefore the local heat transfer coefficient, which usually people speak in case of heat transfer, convection heat transfer, this is nothing but A is related to the temperature gradient at the wall, K del T del Y, Y is equal to 0. This is a local property, temperature gradient divided by TW minus T. This is a very important formula. That how the heat transfer coefficient is related to the temperature gradient. This is because the basic mechanism of heat transfer from the plate to the fluid is by conduction only. Okay. Now we define a average heat transfer coefficient. Now if we have to find out Q, total heat transfer, what you have to do? You have to integrate Q with the dA. That means in terms of H, if you have to integrate H into TW minus T infinity into dA over the area A, or any area over any finite area, or it can be written in this way also, minus K del T del Y at Y is equal to 0 dA. This is very simple because I know per unit area and then I have to integrate with the area. Now final integration will depend how the area varies. That becomes the problem of mathematics. So this is the total heat transfer from a finite area A. So a average heat transfer coefficient over a finite area A is defined as the total heat rate of heat transfer over the area A divided by A into delta T reference. That means if you put this delta T reference, I will not use here, this is in general terminology. Here straightforward I write TW minus T infinity in this case. So if you put now Q like this, then H bar is area averaged heat transfer coefficient. In a flat plate here with a constant width in the direction perpendicular to the plane of the board, it is simply an arithmetic mean over the length H dx 0 to L, because here dA is dx into B. B is the width of the plane. So it depends upon the type of the surface. So rest part is nothing but mathematics. So the way we define the average heat transfer coefficient over an area, it boils down to the fact that average heat transfer coefficient is nothing but the area averaged local heat transfer coefficient. So this is the way we define the heat transfer coefficient in a convection heat transfer, which is related to this temperature gradient. Now this is true for both forced convection and free convection. Let us now consider a free convection case. Exactly, the entire thing is similar, only this picture will be different. If you consider a free convection, there are several situations for free convections, but I give you a classical example which I already told earlier. If there is a vertical plate which is at temperature TW different from the temperature of the surrounding fluid in quiescent state T infinity, and let us consider that TW is greater than T infinity. I told you a motion like this will be set up because of the buoyancy due to the temperature difference. A motion which is shown like this, the air will flow like this. How it can be explained? It is the chimney effect. Very simple, that if you take 2 points at the same horizontal line here A, and at the same point very close to B, the pressure here, hydrostatic pressure, is higher than this point because of cold column of air. That means any arbitrary reference horizontal plane above this, if we take 2 points vertically above B and vertically above A, the pressure here is the pressure at this point plus the rho gh, the hydrostatic head, with respect to this cold column of fluid, which is at higher density. Whereas here this pressure and this pressure is same at the same horizontal plane, hydrostatic pressure is same. It is this pressure plus the hydrostatic head, that is rho gh, where rho pertains to the density of a hot column of fluid. Consider air. So therefore this pressure is lower. So therefore PA is greater than PB, and this is the mechanism by which this type of flow takes place. If this is at lower temperature than the surrounding fluid, this is the reverse direction. The flow will come from the top to bottom. So what happens? Because of the buoyancy induced flow, whenever there is a flow, the formation of boundary layer and thermal boundary layer because of heat transfer will remain same. So therefore there will be the formation of hydrodynamic boundary layer, and there will be formation of thermal boundary layer also. So picture remains the same. Here the coordinate may be different. If this is vertical plate Y, it is always reasonable to give the Y coordinate in the vertical direction. Doesn't matter, you can give X. So if you give Y, then X direction heat flux is Q. So therefore the question remains, the thing remains same, and it will be del T del X. So therefore, whether it is a free convection, that is a buoyancy induced flow, or the forced convection, it is a force induced flow. That means flow is induced by external agency. Ultimately it is dominated by the flow field, and the heat transfer from the surface is because of conduction, and that's why we relate the heat transfer coefficient this way with the temperature gradient, where heat transfer coefficient in convection is defined like this. It's clear? Now we try to write this temperature gradient in non-dimensional form. You know the reasons for non-dimensionalization of the variables, which has been taught in detail in fluid mechanics class, I hope, and it will be again repeated. So it is done from both theoretical point of view, that means from the theoretical, in the theoretical equations, and also we can do it by the help of dimensional analysis. What are the non-dimensional terms that come into picture, because it is the non-dimensional term which takes care of the physical similarity, and if you express any phenomena by non-dimensional term, it can take care of several situations with several variables by dumping them into few less number of variables. So with this philosophy we make a non-dimensional approach. So therefore our first attempt will be, let us make a non-dimensionalization of this thing, k del t del y divided by Tw minus T infinity. That means let us first try to non-dimensionalize the temperature. Let us define a non-dimensional temperature in this way, which is the convention for external flow is the surface temperature minus the temperature in the fluid divided by Tw minus T infinity, which varies from 0 at the surface to 1 at the edge of the boundary layer. It is not dependent upon the actual value of Tw and T infinity. So it is normalized. Non-dimensional variable means normalized variable. Let us make y non-dimensional as y dash by using a reference length scale. Let us do that. Then what is the value of del t del y? Del t del y is T infinity minus Tw, T infinity minus Tw del theta del y. Okay, am I correct? And what is del y? It is del y dash L reference. That means it is T infinity minus Tw del theta del y dash divided by L reference. So now if I put this, and it is valid for y is equal to 0 also, in this equation, that means del t del y in terms of a non-dimensional temperature gradient, where the non-dimensional temperature is defined like this, and the non-dimensional y coordinate is defined like this, y by some length scale, reference length scale. Then this is, now if I put there, then I get h is equal to that minus k del t del y at y is equal to 0 divided by Tw minus T infinity. Again I write minus k, it will be easier if I write it here, del t del y at y is equal to 0 divided by Tw minus T infinity. If I now write this, then what you get? You get k by L reference into del theta del y dash y is equal to 0. Now y is equal to 0 means y dash is equal to 0, because I want to have all non-dimensional parameters here. So therefore y is equal to 0 means y dash 0, because y dash is y by L reference, it is scaled with L reference. Then we can write h L reference by k is equal to del theta, a non-dimensional temperature gradient at the wall or at the surface. So this is non-dimensional temperature gradient, that means the left hand side is also a non-dimensional parameter. And if you write the unit, what is the unit of heat transfer coefficient? Heat flux divided by temperature, that means watt per meter square Kelvin. And if you use that watt per meter square Kelvin and K is watt per meter Kelvin and L reference is meter, then it is dimensionless. And this dimensionless quantity is known as dimensionless heat transfer coefficient, and it is known as this HL reference by K is known as Nusselt number. Nusselt number. Okay, this is known as Nusselt number. So here in the derivation of Nusselt number, by expressing, derivation means to have an idea of Nusselt number, we see that Nusselt number is a non-dimensional heat transfer coefficient based on a reference length and K, like Reynolds number, rho Vd by mu, based on rho Vd means D is the hydraulic diameter for internal flow. For external flow, it is the current coordinate or the length of the plate for a flat plate. That means it is a characteristic reference dimension. So based on a reference geometrical dimension, L reference divided by K, and H has a local character, so Nusselt number also has a local character, and this Nusselt number is nothing but the non-dimensional temperature gradient. That means if we can find out the non-dimensional temperature gradient, we can find out the Nusselt number. But here one information you must have, that in case of flat plate, for example this one, if I draw the thermal boundary layer like this, delta T, and let us have this thing T, this is TW and this is T infinity and this is delta T. Now usually the reference dimension for normalizing the y coordinate is not taken anything along the plate. The normalizing diameter is taken as the boundary layer thickness, delta T. So L reference is taken as delta T. So therefore L reference is taken as delta T in this case. So therefore we write H delta T by K is the Nusselt number, which is nothing but del theta del y dash at y dash is equal to 0, where y dash is equal to y by delta T. So therefore where y dash equals to y by delta T. Usually it is scaled with delta T, and in that case H delta T by K is this, L reference becomes delta T, but at the same time it is the convention that the dimensionless heat transfer coefficient H, that is HL reference by K, which is known as the Nusselt number, and this local character comes from the local heat flux, that is the local heat transfer coefficient, is conventionally defined as Nu, for example x, the local point, H into x by K, not delta T by K. So therefore if I rearrange it, then Hx by K is equal to del theta del y dash at y dash equals to 0 into 1 by delta T by x, because I multiply with x by delta T, which goes this side. Okay, clear? So therefore we see a Nusselt number, this is the Nusselt number, Nu equals to the non-dimensional temperature gradient times the ratio of thermal boundary layer thickness to the x, which is also a non-dimensional form of the thermal boundary layer thickness, delta T by x. And these two things are totally dependent on the fluid mechanics, that is the flow field and the temperature field. And this temperature field in turn depends upon the flow field. Temperature field in turn depends upon the flow field. Earlier we have assumed certain things, that for a given Prandtl number, if we have delta as the hydrodynamic boundary layer, we have delta T as the thermal boundary layer, which is connected by a property known as Prandtl number. But how is it connected? How do I get the temperature field? Now the entire essence comes that if I have to find out the Nusselt number based on this heat transfer coefficient, this is the local Nusselt number. Similarly, we can have average Nusselt number based on average heat transfer coefficient. We have to know the temperature gradient at the wall. That means we have to know the temperature field and the growth of thermal boundary layer. And these things are governed or guided by the flow field and the temperature field. So therefore, we have to know fluid mechanics, and we have to know how the flow field affects the temperature field, for which we have to know the energy equation, and we have to derive the energy equation. What is the difference between heat conduction equation? Energy equation is an equation for energy balance. In heat conduction equation, we have considered an element and made the energy balance by heat conducting, heat conduction coming in, going out, energy generation, that's all. Or a convection heat transfer, which we took through only a convection heat transfer coefficient, and we made a balance. But when there is a flow of fluid and we take an element, along with the conduction, we have to consider the advection of energy, which is very important. As I told, that advection of energy, total energy, which comprises internal energy, that is intermolecular energy, plus the flow work. And internal energy, not only the intermolecular energy, kinetic energy and the potential energy, plus the flow work. All these things have to be taken together. Along with that, generation of energy by the viscous dissipation because of the work done against the viscous forces. All these things will be taken, will be considered, will be taken together to derive the energy equations where the velocities will appear, and the velocity field will be given by the Navier-Stokes equations. So therefore, you see, to understand more of the convection heat transfer, we have to know the temperature field, which in turn governed by the velocity and the velocity field. So therefore, a review of fluid mechanics, derivation of energy equations, all will be followed afterwards with this primary introduction to convection. It's clear? So this way we define a Nusselt number, which is Hx by k. Now I tell you that this thing depends upon the flow field and the temperature field, which are guided by two very important parameters. This will again be taught in details, that these are guided by very two important parameters. If we consider the flow to be incompressible, that means whose velocity is, flow to be incompressible, if we consider the flow to be incompressible, whose velocity is relatively much smaller compared to sonic velocity, and we consider we discard the flow of fluid through a very narrow channel, for example in a micro channel or micro tube where the strain rates are very high, we can discard the viscous dissipation. That means dissipation of mechanical energy in terms of thermal energy, and we can tell in that case the fluid mechanics along with the energy equation, that is the temperature field, is guided by these two parameters. One is Reynolds number. Now this is for your information, Reynolds number. Another is Prandtl number. Prandtl number. And Reynolds number, as you know, is defined as reference velocity, reference length divided by the kinematic viscosity, and Prandtl number is defined as kinematic viscosity by thermal diffusivity, momentum diffusivity by thermal diffusivity. And these two non-dimensional parameters we will see afterwards in our theoretical analysis govern both the temperature and the velocity field for usual external and internal flow, where we discard the effect of compressibility in consideration of the flow to be at relatively lower velocity as compared to the sonic one, and also we discard a high viscous flow through a very small microchannel where the strain rates are high, so that viscous dissipation will be high. So if we accept this, then we can tell that Nusselt number, which is the non-dimensional form of the, now I write in a most generic form, L reference, which is x. But in case of internal flow, this L reference is the hydraulic diameter. For an example, Reynolds number, this L reference is x for a flat plate. External flow, for example, over a flat plate. But this becomes the hydraulic diameter in case of internal flow. So therefore, I write in a generic fashion is a function of Reynolds number and Prandtl number. And the entire heat transfer analysis here will be centered on this to find the relationship between Nusselt number with Reynolds number and Prandtl number for such flows, and this relation depends upon the type of flows, whether it is a flow past a flat plate, flow past a aerofoil, external flows, flow past a circular cylinder, or internal flow, flow past a cylindrical tube, or like that. That means depending upon the flow configuration, this relationship will be different. But this Nusselt number will be function of Reynolds and Prandtl. But the question comes for free convection. In case of free convection, you can ask me, sir, there is no Reynolds number in free convection, because in a free convection there is no forced flow, because flow is not induced, a flow is not imposed by an external agency. That means there is no velocity scale. For example, in a forced convection, this V reference is the free stream velocity for external flow, and for internal flow, this is the volume average velocity, that average velocity based on the volumetric flow rate. This we have told in fluid mechanics class, or the teachers have told in fluid mechanics class. But in a free convection flow, there is no reference velocity. This is because the flow is not imposed by the external agency, so we cannot identify a scale of velocity. In that case, what is done, we consider the buoyancy force per unit volume as the mathematical criteria for that, which is the cause of the flow, because it is buoyancy driven flow. And you know that buoyancy force per unit volume is G times the change in the density. Buoyancy means change in the density, and that change in the density usually occurs because of the temperature gradient. As you know, if you hit from the bottom, the fluid will be lighter and go up, and there will be a circulatory motion. That the way I have explained. So therefore, it is the buoyancy driven flow, G delta rho. This change in the density may also take place because of another gradient, which is the concentration gradient for multi-component flow. That means if the medium consists of different components with different concentration, then the concentration gradient may change the density. But we are not going into that complications. Our heat transfer studies are far apart from that. We are not considered that, only a single component flow. So therefore, change in density only because of the temperature gradient. And the heat transfer scientists usually do what they do, usually substitute this change in density in terms of the volume expansivity, in terms of a parameter known as volume expansivity, or volumetric coefficient or volumetric coefficient of thermal expansion, volumetric coefficient of thermal expansion. This is the usual style, but not very universal. When the concentration gradient is there, we don't do that. But usual style is that this is defined as volumetric coefficient of thermal expansion is 1 by V, V is the volume, I use a cut because to distinguish it from velocity, into del V del T at constant pressure. This can be written as minus 1 upon rho in terms of density. We should understand from the change of, because rho V is constant, because rho V is constant. For a given mass, rho V is constant. So therefore, rho del V del T plus V del rho del T is 0. So it is very simple that rho V constant, either this or this. Okay, and this minus sign takes care of the sign of del rho del T, so that beta as a scalar coefficient is always positive. Now if you do that by a first order approximation, one can tell that delta rho, the change in density, is scaled with rho beta delta T. This can be written like that, that delta rho, the change of density for a given change of temperature, with a first order approximation can be written, or it can be scaled like that, rho beta delta T. So therefore this becomes G rho beta delta T. That means instead of a velocity scale, we consider the buoyancy force, or the buoyancy force per unit volume, the buoyancy force per unit volume. In place of the velocity, we consider this in the theoretical equation of motion, in the Navier-Stokes equation. You will see afterwards when you will solve those category of problem. And even in the dimension analysis, we replace the reference velocity with that, and instead of Reynolds number, we come up to another number, so that Nusselt number becomes a function of GR, Grashof number, and Prandtl number. So Reynolds number is replaced by GR, which is known as Grashof. All these people are big scientists, great scientists. Grashof number. Grashof, Grashoff, and this is equal to G beta delta T L reference length cube by mu square. So physical significance of Reynolds number, you know, it is implying, it is proportional to the ratio of inertia to viscous force. So Reynolds number implies the inertia to viscous force, and it represents the dynamic similarity of the flows governed by inertia force, viscous force, and pressure force. And the physical significance is Prandtl number is the ratio of the two diffusivity, relative. That means nu is responsible for taking the momentum transport, that the presence of the plate, its presence of the plate in the flow field. How much the presence of the flow goes to the flow field, what is the extent of hydrodynamic boundary layer. Similarly, alpha represents the presence of the hot surface or cold surface in the stream, which is at a different temperature, how much the influence goes, and therefore this represents the extent of the thermal boundary layer. Therefore their ratio is proportional to the ratio of the two boundary layer. More is the nu, more is the hydrodynamic boundary layer. More is the alpha, more is the thermal boundary layer. Similarly, this Grashof number, this is for your information today, this all will be done afterwards, so that you can enjoy this thing afterwards. This Grashof number is a number which physically signifies, is proportional to, not directly, to the buoyancy force to viscous force. It is exactly not buoyancy force to viscous force, it is the buoyancy force into inertia force by viscous force square. There is a term like that, and where the inertia force is defined on a velocity, a representative velocity scale, which will be derived from the buoyancy driven flow, that is the buoyancy force per unit volume. That I am not doing at the present moment in the introductory class. So this is the physical implication of the Grashof number, which is ratio of buoyancy force to viscous force, but not exactly so. So therefore the entire thing boils down to this fact, to know this dependence, that Nusselt number with Reynolds and Prandtl, we have to solve for temperature field and the velocity field. And for the solution of temperature field, we have to know the velocity, because the energy equation which involves temperature as the unknown dependent variable contains the velocity as the known parameters, which will be fed from the solution of Navier-Stokes equation. And similarly, to know the Nusselt number, this relationship for free convection flow, we have to solve similarly the temperature and velocity field, where the flow is because of the buoyancy. With this, I like to end, and I tell you that for this, we have to know the fluid mechanics in details, and also the the energy equation, the derivation of energy equation, all these things will come and which will be followed afterwards. Before I end, I just show you one, before I end, just as an application, simple, very simple, it will take not more than 2 minutes, a problem like this. There is a flat plate. At a temperature Tw, okay, and there is a cold stream at a temperature T infinity. Now the temperature distribution is given by this, Tw minus T divided by Tw minus T infinity is 2y by delta T minus half y by delta T whole cube. And it is given that the hydrodynamic boundary layer is 5 by root over Rex, where Rex is equal to u infinity x by nu. And also given that delta T is delta. That means nu is equal to alpha. So prove that Nusselt number is 0.4 root over Rex, local Nusselt number, NUX. And what is the value of average Nusselt number? How do you solve the problem? Temperature is a function of both x and y. This is x, this is y. But y is, this x is taken in delta t, similarity parameter, y by delta t. How to solve this problem? Very simple. Let us do this at a direct application of what we have discussed today. Nothing can be simpler than this. Nothing can be simpler than this. How to do this problem? Now, we have to find out Nusselt number. Now, Nusselt number x is h, this is the convention, x by k. How to find out h? H is minus k del t del y at y is equal to 0 divided by Tw minus T infinity. What is del T del y? Del T, this is a minus, that means T infinity minus Tw into 2 by delta T. This term will be 0. That means Tw minus T, so minus will go down. That means minus minus will cancel, equals to K into, what is that? K into 2 by delta T into 1 by, no, that is automatically gone. Del T del y at y is equal to 0 is T infinity minus Tw into 2 by delta T and Tw minus a minus. Okay? So, Hx by K is 2 by delta T by x. Now, what is delta T by x? Delta is 5 by root over Rex, delta T is root over this thing. So, what is this? Delta T by x. Find out. hx x by k is 2 delta t by x. Delta is 0.5 by delta t. Delta is equal to delta t is equal to u infinity x by nu under root. Huh? So, okay. So, delta, what is delta t by x? Is what? 5 by root over u infinity x by nu into x. So, if you put that delta t by x, it will be, is there any mistake? Which one? Delta by x, sorry. I am sorry, it is the non-dimensional delta, it is root over Rex, very good. It is delta by x. So, therefore, delta by x is this. So, therefore, there is no point of doing all those things. So, delta t by x, this cannot be, this is so simple. So, delta t by x. So, this is the expression of delta by x, non-dimensional. So, therefore, if you put that, automatically you get Nusselt number x is 2 by 5. That means 0.4 into. This is root over Rex. We don't have to write in terms of u infinity x by nu. Okay. Now, how to find out the average Nusselt number? You have to find out the average heat transfer coefficient. So, how to find out the average heat transfer coefficient? The average heat transfer coefficient to find out in this case, as I have told, 1 by h dA h bar. That means, in this case, the average heat transfer coefficient as it is defined, 1 area average h dA. In this case, it is 1 by L over a length L. Find out the average heat transfer coefficient over a length L. It has to be prescribed over which area you are telling. That means, about which area it is being prescribed. This is the length L for a given width B. So, therefore, it is nothing but 1 by L h dx 0 to L. And the beauty is that here, this is hx x by k is 0.4 root over u infinity x by nu. 0.4 by root over Rex, I am sorry, by root over Rex, I am sorry. So, that 0.4 by, no, 0.4 into Rex, 0.4 into Rex, not 0.4 by Rex, 0.4 into Rex, root over Rex, okay. 0.4 into root over Rex, sorry, 0.4 into root over Rex. So, 0.4 into root over u infinity x by nu. So, therefore, you find out the heat transfer coefficient Hx is equal to 0.4 k root over u infinity by nu x to the power minus half. That means it is decreasing with x to the power minus half. If you take this as constant, then a beautiful thing you will see that 1 by L 0 to L A x to the power minus half dx. What is the result? Result is, what is the result? 1 by L x to the power minus half plus 1 x to the power half divided by the half. That means 2a L to the power half divided by L, that is 2a by L to the power half. That means this tells you one very interesting thing, that Nusselt number, so therefore HL average over a length L is equal to 2 times the Hx, because the same thing 2a L to the power half, because here A is 0.4 K. That means since it is varying with x to the power minus half, so this is a very good conclusion. I tell you, it's a thumb rule. HL average over a length L is 2 times this local heat, because local heat transfer coefficient is some constant which is 0.4 K root over u infinity nu in this case, because this is the law which we have found out, divided by x to the power half. So if you put x as L, that means it is the local heat transfer coefficient at x is equal to L, and twice the local heat transfer coefficient equals to the average heat transfer coefficient up to that length. That means you can make a thumb rule, very preliminary thing, that if x to the power minus 1 upon n, so it will be becoming n plus 1 times the local heat transfer coefficient. And when it is x to the power minus up, that means twice the local heat transfer coefficient. That means the average Nusselt number over a length L will be 0.8. That means I will write 0.8 into root over Re based on L. Clear? Any question if you ask me? Because this mathematics is very simple. Sometimes doing it hurriedly, some inadvertent mistake is there. That means it is very simple. When you do the mathematics, you see it depends upon exponent of x. So concept is this: area average heat transfer coefficient is the average heat transfer coefficient, and Nusselt number, average Nusselt number over a given area is the average heat transfer coefficient times the reference geometrical dimension L reference by K. Clear? Okay. So therefore today we have appreciated one thing, that to know details about the convection heat transfer and to develop this fundamental relation of Nusselt number as a function of Reynolds number and Prandtl number, we have to know, or Grashof number and Prandtl number, we have to know the flow field and the temperature field, for which we have to recapitulate our fluid mechanics, Navier-Stokes equations, boundary layer equations, and also the energy equations, which in the next class the derivation of Navier-Stokes equations will be taken by Professor Sumon Chakraborty.